welcome you to this lecture on linear hydrodynamics. In the last class, we have talked about the basic equations associated with the linearized long wave, and here we have two equations. One is the equation of continuity and other is the equation of motion. We have discussed this in case of both in case of one dimension and in case of two dimension. Then we have also looked into the case of variable width and breadth. So, today let us work out one example to understand the solution procedure associated with the long wave equations. Suppose I consider the let me say I consider the one dimensional long wave. And I say suppose I have a channel of length rather I will say, and I have length, this is the depth from the mean water depth, this is h, and then the length is L, this is 0, this is L, this is the total length L. So, if I have a channel of length L and the depth of the channel is h, then here we have C is equal to root G h, and further since I have two walls, on the two walls what will happen? I will have del eta by del x, because the velocity will be 0 along this wall. So, that will give me del eta by del x at x is equal to 0 to del eta by del x at x is equal to L, this is 0. Now, I again take two initial conditions. Suppose I have been given that suppose eta x 0, the displacement is f of x at a t is equal to 0 and eta t x 0 is equal to g of x. Suppose these are the initial data at time t is equal to 0. So, in that case what will happen, how we will get, and we are looking into what will happen to eta and then what will happen to u. So, because here once we know eta you can know u or vice versa. So, let us concentrate on knowing what exactly eta is. So, to know eta, so first we will do, we all know that we can always write eta, because this is this conditions are homogeneous conditions, this is a homogeneous equation with the two homogeneous conditions, boundary conditions. So, we can always apply the method of separation variable. So, I can write eta x t as eta x x into t t, and then this will be, if I substitute for eta in this one, then I will get x double dash x into t t is equal to 1 by c square t double dash t into x x, which gives me x double dash x by x of x is equal to 1 by c square t double dash t by t t, and because this is a function of x, this is a function of t. So, I can call this as a constant. Let me say lambda is a constant, the same constant is lambda, and in this, so because if once we say this is lambda, so we will get two sets of equations from this, that will give us x double dash minus lambda x x is 0, and the other equation is t double dash minus lambda c square t t is 0. Of course, this is a function of t, this is also a function of x. So, then if I look at the solution of this, I have three cases here, and in case of so what will happen, we also have been given del eta by del x at x is equal to 0, and that gives us 0, which implies x 0 is 0, and again del eta by del x at x is equal to L is 0 and that gives x dash 0 is 0, and this also gives me x dash L equal to 0. So, these are the two. So, in x, so I have this equation I have to solve subject to these two conditions. So, this is a Sturm-Liouville type boundary value problem becomes in x, and because two end condition, 2 point Sturm-Liouville boundary value problem, because we have 2 points, the boundary conditions are prescribed, and this is a 2 dimensional second order differential equation. And then, so now what will happen to x? So, x will satisfy, my solution of x will be a e to the power root lambda x plus b e to the power minus root lambda x. So, if I substitute for one of these boundary conditions, suppose del eta by del x at x is equal to 0 is 0. So, that gives me a minus b is equal to 0 because of this condition, and again which implies a is equal to b. On the other hand, if I put x dash L is 0, so that gives me x dash L means this will be e to the power root lambda L, then a is b plus e to the minus root lambda L into a equal to 0, and since if a is not 0 implies cos hyperbolic root lambda L is 0. This is a minus b is 0. So, this is x dash L, or that is a minus sign. Yeah, sorry, it is minus because this is x dash L is 0. So, I will rather say x dash L is 0 implies this is equal to root lambda in 0. So, a is not equal to 0. So, we will have which implies sin hyperbolic lambda L is 0. Now, question comes, if lambda is 0, L is non-zero. So, if lambda is 0, then I have implies sin hyperbolic lambda L is 0. So, implies if I say lambda is 0, then I will not have any solution, implies x double dash x is 0, and that gives x is a x plus b, and again that will not be any help to me because I am looking for a solution of in x and t, it should behave like a wave. So, it will not helpful. So, this solution is ruled out, this cannot be a solution because I am looking for wave type solution. On the other hand, if I look lambda is greater than 0, now if lambda is greater than 0, that means sin hyperbolic root lambda L is 0, and so if lambda is greater than 0, that means L has to be 0, L is non-zero. So, lambda is greater than 0, L is non-zero, implies so which implies this term cannot be 0, impossible. This is impossible solution because I have sin hyperbolic root lambda is 0 and L is not equal to 0, lambda is greater than 0, which is impossible. So, this is also another case. So, the only choice remains that lambda has to be less than 0. If lambda is less than 0, that means if lambda is less than 0, then I will have sin, let me say lambda equal to minus p, and if lambda is minus p, so then I can always say, rather I will say lambda is minus p square, which implies root lambda is equal to minus, or rather I will say I p, and then that will give me sin hyperbolic root lambda L. Root lambda is I p L 0, which implies sin p L is 0, and if sin p L is 0, which implies p L is equal to n pi, implies p is equal to n pi by L, thus implies. So, that means my n is equal to 1 to up to, this is n is equal to again 1 to. So, then I call this as p n. So, what happens? So, I got, so sin hyperbolic root lambda L is equal to 0 implies p n is equal to n pi by L, and whereas that gives me, and again we have p n is, we have seen that root lambda, and then in this case because I have for each p n I will get a lambda. So, I call this as corresponding as lambda n. So, root lambda n is I p n, I can call this. This is, that means for each lambda n I can get, and this is called. So, in the process what I will get? I will get my x x as sigma n is equal to 1 to infinity a n sin hyperbolic sin that is n pi by L into x. This is my x part, and then this becomes a eigenvalue problem, and this is called the x x. So, I have infinitely many such eigenvalues, and these eigenvalues are root lambda are the eigenvalues, or p n's are the eigenvalues, and corresponding eigenfunctions are the sin p n L, sin n pi by L into x. These are the corresponding eigenvalues. Okay. So, if these are the eigenvalues, now sorry, x x is not this, because I have started with lambda, these are my lambda n, but my x x is equal to a e to the power a is b. So, e to the power root lambda x plus e to the minus root lambda x, and that will be again, rather I will say a n into the root lambda is I p n, this is I p n x plus this becomes my x n x, and into the minus I p n x, which I can call it as some a n cos p n x. And so, in the process I will have, this is one of the eigenfunctions, sorry, this is wrong. So, this is one of the eigenfunctions, and in the process we have, because superposition of all the eigenfunctions will give me the full solution. So, that will be my x x is sigma n is equal to 1 to infinity a n cos p n x, and my p n is n pi by L. So, that gives me sigma n is equal to 1 to infinity a n cos, in fact I can also take a 0, because that will give me n is equal to 0 I can take, because that will give me a constant also. So, n is equal to 0 to infinity a n cos p n x, where p n is n pi by L. Then what will happen to the s t t? I have t double dash t minus lambda, lambda is again minus p n square, lambda is minus p n square, and that will give me plus lambda c square t minus lambda plus lambda is n pi by p n pi by l into c into t t is equal to 0, and that gives me that t t the solution is, I can also call it cos n pi by n pi c t by l plus d n sin n pi c t by l. So, then this I can call it t n. So, if I combine this with x x, then what will happen, because this is if I look at this, but if I look at the individual x and t n, x and x into t and t also will be a solution, that will give me sigma, that will give me my x and x is a n into c n. So, I can call it some b n or call it a n cos n pi by l into x into cos n pi by n pi c t by l plus, sorry, this is, let us put it this way, this is, I can always call this cos n pi by l into x, and I can call this as a n cos n pi c t by l plus b n sin n pi c t by l. This is my x and x. So, which implies my eta. So, I have infinitely many such n. So, eta x t, my eta x t, that will give me, sorry, sigma n is equal to 0 to infinity cos n pi by l into x, I can call it n pi c t by l plus b n sin n pi c t by l. So, this is my eta x t. So, now I have two constants, two sets of unknowns, a n's and b n's, and to obtain these two sets of unknown, I have again two more conditions, because I have only utilized the condition at eta is equal to that at the two boundary conditions. Now, I have two initial conditions. The two initial conditions gives me, that means my eta x 0, I have eta x 0 is equal to f of x, and eta t x 0 is equal to g of x. And then to utilize this, so if I substitute for this in eta, then what it will give me, sigma n is equal to 0 to infinity a n, because this will give me cos n pi by l into x is equal to f of x, and if I look at this one, that will give me sigma n is equal to 0 to infinity n pi c by l into b n to cos n pi by l into x is equal to g x. So, this gives me the two sets of, this will give me the two sets of equations for a n and b n, and if I substitute, because I will utilize these two results 0 to l, this is one integralizer, that is of the orthogonality criteria m pi by l into x into cos n pi by l into x dx, and that is 0 for m is not equal to n. This is l by 2 if I say m is equal to n is not equal to 0, and this is l if m is equal to n equal to 0. So, if I apply this condition, then what will happen? Then utilize this in this, and then that will give me my a 0. A 0 will give me 1 by L, I mean it is 0. So, 1 by L, 0 to L, f t dt and because I just multiply now it, if I using this again, what will happen to my a n? This will be 1 by 2 by L 0 to L. This will be f t cos n pi by L into t dt, and in a similar manner if I utilize this one, this is like the Fourier coefficient. This will give me 2 by L 0 to L. This is n pi c by L into B. This gives me f t gt into cos n pi x by L dt, and this is called t, this is t. So, if I have this factor, this n pi c by L, I can always bring it to the other side, and that will give me by B n is 2 by L into L by n pi c into 0 to L g t cos n pi by L into t dt. So, these are the a n's and b n's, and once I have this a n b n's, so I will get, as I said, that my full solution is sigma my eta x t is sigma n is equal to 0 to infinity cos n pi by L into x, that is a n cos n pi by n pi c t by L plus b n sin n pi c t by L. So, this is my full solution, where all the a n's and b n's are known in terms of f t and g t, and this is what represents, but each of them, for each n I get a mode, I call them are the eigen functions. This n pi by L, this is called the eigen values, and then the individual functions x n x, t n t, they are called the eigen functions, and sometimes we call them as this, what will happen, this cos n pi by L into x, these are called the modes of oscillation. This is the modes of oscillation. So, this is what, and then and these eigen values, in fact, any computation one will do, as we have seen in case of a series, we have seen earlier in case of a wave oscillation in a tank, we have seen that that how the modes of oscillation plays a significant role, and we have seen that the primary modes are the initial few modes, are the primary secondary modes, or the first few modes plays a significant role. In a similar manner, we will easily see that only it can be easily proved soon that these terms will contribute significantly, and again we know that these first few modes, particularly the A0, B0, A1, B1 in the series, first modes of oscillations are these constants, initial constant will play a significant role compared to the unknowns or the constants a n b n for large n. In fact, we can see that I will say rather the series is, of course, the series will converge to this point, and in that case n b n they will tend to 0 for large values of n. In fact, that is what also we will find out from the theory of analysis, that the a n b n will tend to 0 as n tends to infinity. That is sometimes known as the Riemann-Lebesgue lemma in theory of analysis. So, this is what I want to say, this is one of the simplest way to find the solution of a wave propagation problem, and the conditions are very simple, provided f x and g x are known, we can always find that what exactly the form of eta, and once we know eta, then easily we can obtain what is u, because eta is related to with u by the equation of long wave equation of continuity or the long wave equation of motion. So, this is one of the best example to illustrate the solution procedure. With this, now let us go to talk about long wave with bottom friction. Long wave with bottom friction. So, in case of long wave with bottom friction, what we will talk about here, rather in this case the equation of continuity will change del eta by del x, because when there is a bottom, del u by del t is equal to minus g del eta by del x. This used to be the case in case of the equation of motion for the long wave, but if there is a bottom friction, then there is another term which is added to this is a u, and that what is that a u term, where u is the velocity and e is a constant. That constant is again f of u m by 3 pi h, and this is called a small number less than unity, and this is called Darcy-Weisbach friction factor. So, the details one can refer to the book of Dean and Dalrymple for detailed reference. Water wave mechanism for scientist and engineer by Dean and Dalrymple, which I have already prescribed. So, this is a constant, the a will depend on. So, we have this becomes the equation of motion, and in fact, this constant a is a small quantity, it is less than unity, but that will contribute because of the friction factor. Then and again we have the continuity equation, that is h del u by del x plus del eta by del t 0. This is our equation of continuity in case of long wave. If I combine these two equations, or if I eliminate eta, that will give me del square eta by del x square plus a del eta by del t square plus a del eta by del t is equal to g h del square eta by del x square. This becomes my equation of motion in case of when there is a bottom friction, and where a is given by this number and depends on the u m becomes the maximum speed, and f is a factor which depends on the bottom friction, particularly f is called the this is basically the friction factor. So, this becomes the equation of motion for the long wave, and we say if a is equal to 0, this is same as the long wave equation in case of one dimensional. Now, look at analyze this. To analyze this problem, let us consider two separate cases. Suppose I am looking at a standing wave. With frictional damping. Then let me say that suppose my eta is equal to h by 2 into f of t into cos k x. Then what will happen? If I substitute for this in the equation of motion with bottom friction, then that I will get d square f by dt square, because my original equation del square eta by del t square plus a del eta by del t is equal to gh into del square eta by del x square. If I substitute for eta is this, then I will get f double dash t plus a f dash t, and that is gh is nothing but my gh is c square, and this will be del square eta by del x square, that will k square, and this will give me plus k square c square into f, and this nothing but c square k square is nothing but omega square or sigma square. So, or that will give it f double dash t plus a f dash t plus sigma square c is equal to sigma square f is 0. And if I look at the solution of this equation, that solution will give me eta x t, because this is my f t rather, the f t, and with theta if I look at it, I will easily say this is s by 2 and then into a minus a by 2 t into cos of sigma 1 minus 1 by 4 a by sigma square into t into cos kx. In fact, this will be the solution. Basically, we can solve this as a algebraic, look at the characteristic equation and the root of the equation will give us this, and then we can easily see that this is the form of the solution. And here we have taken my sigma is kc, because c is sigma by k, and that itself, so sigma is basically the frequency of the wave. So, now what will it do and what will happen to u? So, if this is my eta x t, then again now let me analyze this term. If I analyze this term, suppose when this term is cos sigma into 1 minus, suppose what will happen if sigma, if this term is greater than 0, that means 1 minus 1 by 4 a by sigma square, if this is greater than 0, then only I have this form of solution, otherwise this will give me a hyperbolic term, and if this gives me a hyperbolic term, then this will not represent, it will not satisfy the wave type solution, and then my purpose will not be solved. So, then this will dominate if it is. So, this has to be greater than 0, and if this has to be greater than 0, that means 1 is greater than 1 by 4 a by sigma square, which implies a by sigma square 1 by 4 has to be less than 1, which implies I should have a by sigma should be less than 2. So, this is one of the criteria that I should have a by sigma, it should be less than 2. And if sigma r is 0, that means if I say, that means a by sigma, if it is a by sigma is 2, if a by sigma is 2, if a by sigma is 2, then in that case the term will not contribute. In that case I will have eta t is a to the power minus a by 2 into t into cos k x. This will be my eta x t. and in that case now what will happen to if I say eta t x t plus t, where capital T is the period, then this will give me a e to the power minus a by 2, t will be replaced by t plus t into cos k x divided, if I divide it by eta x t, this also will divided by eta x t. And that gives me a e to the power minus a by 2 into t, and a is a by 2 t, and t is nothing but when t is 2 pi by sigma, this is the period. So, then it will give me a e to the minus a by 2 into t is 2 pi by sigma, and that gives me that will give me a e to the minus pi a by sigma, and that is what. So, I will get, so this is the, now it can be easily seen that if a by sigma is 0.05, then we can see that eta x t plus t by eta x t, that will give me 0.85. So, what does it shows that over one period eta, that means when this was my elevation and after one period t is the period of this, then when it reaches here, the elevation will reduce by 15%, that is what is. So, that means if, and when I have taken a by sigma is just 0.05, that means when sigma is how small is, how whatever small it is a very small quantity. For these small values, again under this condition that this a by 2, this is what I am getting. That means when, that means sigma is a small, a is a small quantity, even if a is small, that contributes significantly to reduction of the amplitude of the wave when there is a bottom friction, because over one period it is reducing by 15%, that is what it is. In fact, it is because of this reason in many situations, particularly during storms such as tsunami, when a wave propagate to the land area, large amount of, it is always suggested to leave lot of open space, because the open space will reduce the energy because of the friction, and that energy dissipation will be very fast when there is a bottom friction. So, because of that, it is always suggested to leave lot of open space along the coastline, so that it will reduce lot of energy and due to by dissipation. Now, I will look at the corresponding case in case of a progressive wave. This is the case of a standing wave. How the bottom friction takes place in case of a progressive wave with bottom friction. In this case, I will look at a solution of this form, because from the previous experience I always can say that let me look at a solution of the form h by 2 into the power minus k I x into cos k r x minus omega t. And if you substitute this form of solution in the long wave equation with a bottom friction, then one will come across, one can easily see that that this k I k r satisfy the relation c square into k I square plus k r square is equal to omega square 1 plus a by omega square. So, since which we can always write it as okay. So, this will give us two equations. So, here what will sorry, if this is the form of the solution, then if I substitute, because here I have to know what is my k I, what is my k r. Let me just I will come to this. I have to know what is my k I and what is my k r, and then if I substitute for this in the original equation, what it will give me, that it will give me my k r is in terms of k I is k I by root 2 into 1 plus a by omega square root over plus 1 to the power half. And again if you simplify this, then you will get k I, because a by omega is assuming it is small. So, we will get it k I into 1 plus 1 by 8 into a by omega square. This is what one will get, and this is only, this result is valid only when a by omega is small, and here again what we are writing here, k I also will be omega by root g h. In addition, we can say that my k I will be so k r is in terms of a k I. So, again further if I look at this, substitute for this k I in terms of okay, then another relation I have k I, small k I is omega by g s. On the other hand, I have a small I. So, my small k I will be k I by 2, k I is omega by root g h, this is k I by 2 into 1 plus a by omega square root over minus 1 to the power half, and this is nothing but equal to k I by 2 to a by omega. So, this is my, so I have one is k r, one is k I. So, my k r is given in terms of this is my k r, and I can get my k I as this, where this k I is given by this. So, once I know k I and k r, so what will happen to eta x plus L by eta x minus L? I just look at here what happened to here over one wavelength, L is the wavelength. So, then what would happen? This will give me, if I substitute for h by 2 e to the power, h by 2 will get cancelled, that will cause k r x, because k r x is 1 plus a by omega, that will not change because over one period. So, only factor will change e to the minus k I x by x plus L into divided by e to the minus k I x. Second term will contribute to 1, that will not contribute. So, this will give me e to the power minus k I L, and L is 2 pi by So, that again that will give me into the power minus 2 pi my k I by k r. Okay, so again small k I is given my, I have already given my k I is k capital I by 2 into a by omega. So, if I substitute for this will give me into the minus k I is k I by 2 into a by omega k I by k r into k I L minus k L. Oh, sorry, lambda is 2 pi by k. I am sorry. So, we have L is 2 pi by k, L is 2 pi by k, and that k I call it as k r. So, this will be e to the power minus k I into 2 pi by k r into k I. K r is equal to k I, because k r is k I in terms of, because this term we have k r is equal to k I for small a by omega, because there is a term, then it will be 2 pi by k I k r, and that will give me e to the power minus 2 pi into k I by k r. This will what, and again k I by k r, k I by k r, we have k I by k r. So, it can be easily seen that this is equal to into a minus pi into a by omega, because of the other relation k I by k r relation. Once this is there, then what we will do here, because again in a similar manner we will see that when a by omega is small, this quantity will be a very small quantity. So, then what will happen to eta x plus L t, that will be e to the minus pi into a by omega into eta x t. So, that means over one wavelength, again we can see that when it covers from x is equal to, if it is x is equal to 0, this is L, this is the L is the, this is the L is one wavelength. So, when it the wavelength, the wave passes from over, just crosses one wavelength, then immediately there is a factor, this factor will reduce the amplification of the waves. Basically, it will reduce the amplitude of the wave exponentially. So, however small it is a by omega, if a by omega how small it is, but this factor will again bring it, because there is a factor e to the minus pi into a by omega, exponentially it will reduce. So, the wave can dissipate very fast. So, whether in the last example we have seen that when there is a wave which is propagating with time, because we have taken a standing wave, but we have seen that eta x plus t, eta t plus t by t, eta t, there we have seen that with the time it decays, and also we have seen in this example that with the space also the wave nature decay, particularly the amplitude of the wave will decay, that means due to frictional damping. So, this is this is in case of a long wave. There are other ways what also we can show. Suppose I say that if there is a bottom friction, instead of bottom friction, suppose I have bottom porosity. If I have bottom porosity, particularly sandy bed or muddy bed, if I have bottom porosity, then because of there will be a frictional damping. If this is the wave that is propagating, frictional damping. So, in a sandy bed also frictional damping will take place, and then because of fine pores there can be energy dissipation will take place, and also will have a frictional damping. Again this is case of a sandy bed, sandy porous bed. Also we can say that same situation will happen. One of the typical example is that. Another is that suppose we say that we have a muddy bed, sometimes we call it a viscoelastic bed, or poroelastic bed. Then also we will see that due to the deformation and energy dissipation will take place, deformation and dissipation and porosity, whether it is a poroelastic bed. In this case also, particularly sometimes in the theory of mud, we define this as a, the bottom bed is often defined as a poroelastic bed or a viscoelastic bed. So, even if in situation where this situation, when we have a viscoelastic or a poroelastic bed, then also wave energy dissipation takes place. This is a little complex, but it can be easily shown that energy dissipation takes place on a viscoelastic bed, particularly on a muddy bed, or even if on a sandy bed very fast. But sandy bed will be energy dissipation will be if it is a sandy porous bed, then energy dissipation will be very fast, because it is a, there is a friction that takes place due to the porosity in the bottom bed, and that decays the. So, it is because of all these reasons in the coastal area, particularly the wetland areas, or even if the beaches, often large amount of wave energy get dissipated. In fact, it is one of the reason why it is always advised in the coastal area not to destroy the natural beaches, because beach provides us a very wave observing, it has a very wave dissipating, it acts like a natural wave dissipating device. So, it is always measures are taken to protect the existing natural beaches, and often government, and even if government takes various steps to protect the beaches, not only for tourist attraction or human activities, or particularly for sports and other things, or recreational facilities, but it directly or indirectly help us in saving our coastline, because of the large amount of sand which has porosity, it helps in dissipating lot of energy, wave energy. So, that is why this is one of the simplest example I have shown, but this is a little complex, and I think if time permits I may go for this sand porous bed, but this I will not go, and perhaps this will be a little more complex, and it will beyond the existing syllabus what we are planning. So, with this we will stop here. Thank you very much.